Okay, so today we're going to do some exponential word problems. This will be fun. Because they're normally fairly lengthy, I typed them up for you so that you don't have to worry about writing the problem down. We can get right into solving. There's two components to this. You've done problems like this already in pre-calculus. However, what you didn't do in pre-calculus is talk about where the formula came from. You were just given this grandiose, beautiful formula and started plugging and chugging and answering all kinds of questions. In calculus, however, we can actually talk about where that formula comes from. Okay, so separable differential equations, law of growth and decay. Okay, so you should be able to understand the Purdy equation. Does that sound familiar? Yes? Yeah, good. So that's in pre-calculus. Recall you were given that equation. You talked a little bit about what E was, and then you just went and plugged and chugged and solved a bunch of problems. In calculus, however, we're going to talk about and go in depth into where that formula comes from. In other words, step 2, we're going to derive that, and then today, be nice to everybody, okay? It's Tuesday. Okay, so you may have seen it in that form, P equals P naught E to the RT, where P naught is your starting amount of something, whatever it is we're dealing with. E is E. R is the growth rate or the decay rate, depending on what we're talking about. T is time. This is coming back to you, yes? Now, you may have seen it in a different form. You may have had A equals PE to the RT. And in fact, we're going to use some variations down there at the bottom. In particular, we'll probably use the left one, Y equals CE to the KT. The variables are the same. So in that one on the left, C is the starting amount. K is the rate, whether it's a growth or a decay, and then T is always time. And then the right one we'll get to in a little bit. Okay? So where does this pop up? Anything that grows exponentially. I've got 3 examples for you. One involving bacteria, one involving radium, and one involving Newton's law of cooling. Okay? But it applies to anything that involves an exponential growth. Spread of disease, the spread of zombies, radiation decay, okay, that kind of stuff, whether it's a growth or a decay. All right, so we're just gonna get right into it. So first time through, I'm going to take you through all the steps and explain where the Purdy equation comes from using this bacteria example. The second one, we'll just plug and chug into the Purdy equation. The third one is a variation that we need to do a little bit more work on. Okay? And away we go. All right, so what do we know? I need to make some notes here. We started with 600 bacteria, right? And then it grew to 1,800 in 2 hours. Okay. That's some information we're going to use eventually. But there's a little sentence in there that says what? Bad, loud, and proud, please.
The rate of increase is directly proportional to
Stop. Rate of increase. So as soon as we see a rate translates into a derivative. So the rate of increase, okay, so that would be dy, well, we could use y, what do you want to use? Y, B, Q, L? Do you care? Y? Y works fine. Okay, so what is y? Y is the number of bacteria. Bacteria. All right, dy dt. All right, the rate of, I'll go back to where you left off there.
The rate of increase is directly proportional to the number of bacteria.
Okay, directly proportional to, which means we need a proportionality constant. We usually use K for that. Okay. Directly proportional to the number of bacteria. We define Y as the number of bacteria, and so that gives us a rate equation. Because again, we're talking about the rate. And this will probably, in fact, not probably, this is a growth problem. The bacteria is growing over time. We have 2 goals in this problem. One is to come up with a general equation, and once we get the general equation, then we can answer all kinds of questions. Actually, there's only 2 questions we're going to ask. After X number of hours, how much bacteria do we have? And how much bacteria will we have over X number of hours? Does that make sense? There's no other question to be solved here. Okay, so now the calculus kicks in. What do we do first? Always
Separate integrals.
separate. Now, let's talk about all those letters up there. Y is our variable. What's t? Time. Is t a variable? Yes, it is. What about k?
No.
No, that's a constant. Okay, good. So, I'm going to do this. Now, could I have taken the k with the y? Yes, I could have, but that gets a little messy. It's easier if you leave it there. I'm good to go. I've separated my differentials. What's next? Integral. Okay, let's do the easy one first. What's the integral of 1 over y? Natural log y. Good. And what's the antiderivative of k dt?
KT.
Good. kt. Oh, wait. kt.
Let's see.
Good. Okay, and that's an important step. Is everybody following that? Way back when we first started integrals, I said you got to have that differential in there. And again, as I talked about before, a lot of you chose to get rid of them. But in this case, it becomes important because it tells us on that right-hand side what the variable is. The variable is t. So we're taking the antiderivative of a constant, so therefore we get k times t. Just like if it was 2, the antiderivative of 2 would be 2x. Okay so far? Beautiful. What do I get y by itself? Yeah, do the E2 trick. Or you could do the conversion if you're better at that. Okay, now notice what I did there. I skipped a step, but I want to make sure. Is everybody good to go here? If not, speak now or forever hold your peace. You're good with that? Okay, good. Because I think we talked about that the other day, so we should be okay with that. What's e to the c?
C.
C. But just because I don't want to confuse anything, we're going to leave it as e to the c. All right. Now, nothing else I can do with that. I solved for y. Now I need to use the information that you're given in the problem. I know two things. I know that when t equals 0, y equals 600, and I know when t equals 2, y equals 1800. How many variables in this equation? There's actually 4. Y, k, t, and e to the c. Even though it's a constant, we can still find the constant. So I got to do a couple steps here to eliminate things. I'm going to use this chunk of information first. Okay. When t equals 0, y equals 600. So I'm going to come up here, and I know that I'll have 600 bacteria when t equals 0. What's e to the k0? 1. So therefore, e to the c is 600. Okay so far? Now that makes sense from what we know from the Purdy equation already from pre-calculus, that the starting amount is that constant out in front of the exponential. Okay, we just explained, however, where that comes from using calculus. The other chunk of information we're missing in this is k, which is also known as the growth rate, or the decay rate, depending on the problem. How do I solve for k?
The other data.
Beautiful. Can you be more specific?
Yeah. When t equals 2, y equals 1800.
You're going to need your calculators, by the way. These numbers get ugly. Lauren, what's the first step in solving that blue equation?
When you simplify everything and then you put something.
Yeah, also known as Dividing, good. What's next, Lauren?
So me?
Yeah.
Natural log.
What's the natural log of e to the 2k? 2k. And then the last step, Lauren?
Just put it into your calculator.
Not yet.
Not yet.
No.
Divide by 2.
Like it. All right, so type that monster into your calculator. These seldomly, if ever, come out to be nice numbers. The rates are usually something weird. You should, however, get a positive value. How do I know, other than the fact that I'm a professional, how do I know that the natural log of 3 divided by 2 should be a positive number? Say again, I'm sorry? It's increasing, correct. It's a growth rate. Growth rates will have a positive value. Decay rates will have a negative value. All right? What is that number? No? 0.5. Give me 4 decimal places.
549.
5, that's 3.
5493.
5493. 0.5493. It doesn't matter what you take it out to, you want to store that number. This is crucially important. When you start looking at exponential functions, you want to use as accurate an answer as possible. If I take that out to 4 decimal places, I get a pretty good answer. But it's not going to be perfect. We want it perfect, so store that number. And you can store it wherever you want. Store it into K, store it into X, store it into any one of the other 24 letters. I had trouble doing 26 minus 2 there. Okay. So now we have enough information to write a general formula for that problem. Now I know that y is equal to 600 times e to the 0.5493t. That's my general equation. And notice, only 2 variables, t or y, which means you given one, you solve for the other. So let's do an easy one. In fact, I think it asks you on the problem. What's it say? 4 hours. Plug in 4, see what you get.
Like 5400.
Answers?
5400.
5400 exactly. Yes. Gee, you'd think I planned it that way. 5400 what?
Bacteria.
Bacteria. Very good. Okay, that's the first type of problem. Second type of problem might be something like, okay, so let's imagine this bacteria is a disease. And if the bacteria level in the body reaches a certain quantity, let's say 15,000, it'll kill the person. So how long do they have until they crow?
4 hours.
No. No, I said 15,000.
Oh.
Yeah.
No.
So then put 15,000 in for y, solve for t, and you should have the skills to do that, yes? Okay, so there's a lot of calculus involved in this. Now I'm guessing last year in pre-calc, you probably went to the Purdy equation, plugged in 600 for P naught, because that's your starting amount, solved for the rate, because you could do that because you had done logs, and then went forward from there and plugged in chunk. Sometimes I will ask you to derive the formula, other times I'll just ask you to go right from the Purdy equation. So let's do the radium problem using just the Purdy equation. Before we do that, we need to talk a little bit about some chemistry. I think it's chemistry. Many of you already know this, but do you understand how a half-life works? Does anybody not? Because I'd be happy to explain it, but this is a crucial point. If you don't be bashful, raise your hand. We're good. Do you know what a doubling life is?
It's the opposite.
It's the opposite, correct. So a doubling life comes up frequently in investments. I want to invest $1,000 at a certain interest rate. How long will it take me to double my money? Half-life usually comes up with radiation. Okay? How much radiation is left, or how long does it take for half the radiation to disappear? And that becomes crucial in things like Chernobyl. You all know what Chernobyl is, right? I mean, not? It's a Russian nuclear power plant, had a meltdown, irradiated a whole big chunk of area in Russia with certain doses of radiation. And so they can do calculations because they know at what level can humans safely live. So they want to calculate, well, how many years will it be before we can actually move back into the area? So that happened, I think, the late 70s.
1986.
Thank you very much. How do you know that?
I watch TV.
Oh, okay. So 1986, and they said,
Wait for the exact date back.
Casey's moving to Russia. But not yet, I don't think it's safe yet. But they are starting to go back into the area to start looking at those kind of things. They had a similar meltdown in Japan.
Oh, that.
Okay, just thought maybe,
Nah.
see, give you, throw you a lob pitch and see if you can knock it out. But they had a meltdown in Japan, so one of the solutions in Japan is they built a giant dome over the nuclear power plant to try and contain it. It didn't go so well. If I remember correctly, it kind of melted the dome. But anyways, all right, so instead of deriving, we're going to take this one right from the Purdy equation and move forward. If you get confused with the variables, then pick one and stay with it. In other words, in the previous problem, I did e to the kt with a c in front. Now all of a sudden I change a c to a p, I change a k to an r. If that confuses you, then pick one and go with it. So what do we know about radium?
It decays exponentially and has a half-life of 1,600 years.
Good. It has a half-life of 1,600 years. Okay. The problem is, if you ignore the previous problem, if we just work with this information, it doesn't seem like I gave you enough information. Well, how much radium are we starting with? It doesn't matter. Why doesn't it matter? Well, let's suppose we start with 4,000 tons. After 1,600 years, how much will I have left? Half of that, right. So it doesn't matter what I start with, because the first step I'm going to do, like I did in the last problem, is divide. So in other words, I can skip from here to here. Does that step make sense to everybody? We good? Again, you don't need to know what you start with, because when the first thing you're going to do is divide. Now, if it's a doubling problem, instead of having 1/2, you'd have 2. And it doesn't have to be a doubling problem. It could be a tripling problem. It could be whatever you want, but we get to that. Okay, so what do we know? How many variables in that equation? 2. And I know one of them. So 1/2 is equal to e to the 1,600r. Solve for r, please. Answer positive or negative? Negative, because it's a decay. Eli, what do you got?
I got negative 4.33 times negative 4.
Or if you prefer, you could write it as negative 0.000433. It doesn't matter, it's the same thing. But again, store that into whatever variable you want, because we're going to use the stored value. Okay, which means I now have a general formula for radium Well, at least I know the rate here, 10.000433 t. What's part B say?
I don't think we finished A yet.
Oh, we haven't. Oh, I'm sorry. Hold on. I did give you a starting amount, 50 milligrams. Okay, so now we're good. And now we're back to, and again, this is our general formula. Now we're back to the same general formula I had for the last problem. Only two variables, so only two questions to ask. And in fact, the first question says, the amount, and then how much, when will the amount remaining be 20 milligrams? How long will it take for 50 milligrams to turn into 20 milligrams? This becomes then 20 equals 50 e to the negative 0.000433 t. Now, before we do any calculation, stop what you're doing and listen to my question. Will my answer be bigger or smaller than 1,600 years?
Bigger.
Explain to me why. Good. I heard enough people give me the right answer. Yeah, it's less than half, so it's going to be greater than the time that it takes to get rid of half of it. All right, now solve for t. What do you got? 2,115.08. You disagree?
I got that.
2,116.14487.
Yeah.
I got
really
15.
tight over.
Well, there's a discrepancy there. There's a big difference in a year. Which one is it?
15.
15? How many people got 15? All right, sorry. We're going with it.
Just write them, and we all move in.
Also on these types of problems, you have to be careful with your final answer. Sometimes, in this case, we could take that all the way out to 4 decimal or 3 decimal places like you're supposed to. However, it usually says in the problem to the nearest year. When you're doing the previous problem, where you have bacteria, you want to take whole answers because you're not really going to look at portions of bacteria. Some answers can have decimal answers, some answers cannot, depending on the problem. Okay, any questions so far? I think you'll all agree it's a little bit easier when you just plug and chug into the Purdy equation. However, the last problem illustrates a situation where you can't just plug and chug into the Purdy equation. Okay, Newton's law of cooling. So, same Newton that created calculus also did the, what do you call those things? The laws of, yeah, and motion. We have, what are the technical terms? Not the laws of motion, I'll think of it.
Newton's 3 laws, right?
Doesn't matter. He also did this law of cooling thing. You don't need to know Newton's law of cooling because the problem talks you through setting up Newton's law of cooling. Okay? Amanda, can you read that to me, please?
According to Newton's law of cooling, the rate at which an object cools is directly proportional to the difference in temperature between the object and the surrounding medium. If an object cools from 125 degrees to 100 degrees in half an hour when surrounded at an air temperature of 75 degrees, find the temperature at the end of the next half hour.
Oof. Okay, so does it give you any variables to use in there? It doesn't say what to. Okay, so we need to make up a variable. just because we've used it before, I'm going to use y to be the temperature. Now, you might be saying to yourself, why are we using T for temperature?
T is
That's
time.
time.
Because T is time, correct.
Yeah.
Okay. So let's go back to the original statement. You can skip the according to Newton stuff, but it says, what's after that?
If an object cools from 125.
No, before that. Because I got to get a general equation set up.
Okay. Directly proportional to the difference in temperature. So the rate at which an object cools.
Okay, stop. The rate at which an object cools, so the change in temperature, or the rate of change of temperature, is directly proportional to
The difference in temperature between the object and the surrounding medium.
the difference between the object and the surrounding medium. But doesn't it tell us what the surrounding medium is?
At a temperature of 75 degrees Fahrenheit.
75 degrees. Okay. There we go. Doesn't really fit into the Purdy Equation model, so we're going to have to derive this one. And then there's a bunch of other stuff in the problem, too, that'll help us find these variables, right?
Yeah.
Okay, so that's enough to get us started. Separating differentials again, I get 1 over y minus 75 dy is equal to k dt. Take the integral of both sides. This we talked about already, kt plus c. What's the antiderivative of 1 over y minus 75? What does that mean, man?
Nothing.
Oh, you're working on your
No.
voguing?
I was.
You guys know the Vogue? No, is that too young? You know, Madonna, Vogue?
No, we know that.
You do, okay, just checking.
Never mind.
Okay, good. Let's go back to my question then. What's the antiderivative of 1 over y minus 75?
Natural log of y minus 75.
Good, natural log of y minus 75. I will mention that you all realize that that should be done as a UDU, correct?
Yes.
Okay. Again, I don't want you to get in the habit of anytime you see 1 over something, you think the antiderivative of that is just the natural log of something. It's a little bit more complicated than that. Okay, e to the y minus 75 is equal to e to the c times e to the kt. All right, Amanda, let's see, what kind of information do we have then? What's our temperature when we start? Let's use that first.
125.
Okay, so we're starting with 125 degree temperature, which means that, get rid of this, when t equals 0, y equals 125. So 125 minus 75 is equal to e to the c times e to the k0, which means that e to the c is 50. So now we're back to y minus 75 is equal to 50 e to the k t. Okay, change colors again. All right, what's the next chunk of information?
Well, it cools from 125 to 100 in half an hour.
Cools from 125 to 100
In half an hour.
in a half hour. So the temperature is 100 minus 75 equals 50 e to the 1/2 k. Is that right? You said 100 degrees in a half hour. Okay. Beautiful. Careful on that too, by the way. The College Board likes to throw in things like 30 minutes instead of a half hour to see if you're paying attention with units. Sneaky sons of guns. 1/2 is equal to e to the 1/2 k. So k is equal to, will k be positive or negative? All right, well, let's see. By the way, I keep skipping this step because I'm assuming you're okay with solving for k in this case. Is that accurate? Take the natural log of both sides, divide by 1/2. And k turns out to be, say again? Or don't. Or just sit there quietly and be afraid to talk. Negative 1.386. Store. Don't just use that. Okay, which means, slide this guy up, change colors to that ugly color. Y minus 75 is equal to 50 times e to the negative 1.386t. There's my general equation. And again, we can answer all kinds of questions. What's temperature of it at 6 hours? How long will it take for the temperature to reach 65 degrees? Let's do that one. How long will it take for the temperature to reach 65 degrees? Why? I did. Yeah. You've got a couple of you. Why can't it reach 65? Let me ask a two-part question. Mathematically, why can't the temperature ever get to 65? What did you say? Yeah, you would end up getting the natural log of a negative number, which we know doesn't work. I guess this would be chemistry, right? Chemistry-wise, why can't it be 65?
Because the surrounding area is sitting to it.
Right. It can't get lower than the surrounding temperature.
But I guess it's like common sense wise.
I wouldn't, you assume way too much, right? Yeah. You can't put a cup in a room and expect the temperature of the cup to cool less than the room you're in. It just doesn't work that way. Okay, unless there's some freaky reaction going on, which I wouldn't understand anyway. Okay? Questions? Are we good? All right, so, still trying to get caught up. We're still a day behind. This will get you going on most of these equations. Again, knowing how to get the Purdy equation is half the battle, because some of the problems aren't going to just be Purdy equation plug-inable. That's horrible English, but you know what I'm talking about. Okay, tomorrow we're going to do, aside from our day 100 party tomorrow, in case you forgot, it's pretty much going to be a work day. There is another assignment. However, that other assignment is more of the same thing, practicing separating differentials, not necessarily word problem. The homework from Friday, hopefully you didn't finish it because it was a no work weekend. Tweak that, get that fixed up, and then do this stuff tonight. Tomorrow in class, we'll basically sit around and eat and do problems, and drink and do problems. Question?
Can you pull up the 100 days thing?
Certainly.
I don't know if you can do it, but if I